Okay, I'm going to be a little rusty with doing video lessons, but we'll just get through it. So I just want you to watch this video lesson, take notes like you normally would. It's going to be on universal gravitation, and then work on the questions posted, which I can. It says Wyatt. I'm not sure why it says that. Work on the questions. Questions. There you go. And then email me if you have any problems. And I will save it like that. All right, that looks a little better. Sorry about that, Wyatt. Um, I'll show you what the questions are after. Let's just get right into the PowerPoint, I guess. So yeah, you'll have to pause this. I don't know. You guys are probably rusty at learning from lesson videos as well. I'll make sure my writing tool works. It does. That is good. So you're watching this either on a Chromebook or your phone or whatever. Just pause this as we go if you need to pause it, and so that you can keep up. I will warn you, I don't have a calculator or a scientific calculator at home, so I probably am not going to get final answers to a lot of these. Now, you might be thinking to yourself that, hey, didn't we do the force of gravity? Isn't it just Fg equals mg, where this is the mass and this is, typically 9.81 for on Earth? Yeah, but that's only good if you know the gravitational field strength at the surface of whatever planet that you're on. The universal law of gravitation is going to be good anywhere in the universe. All right, it's a little more ugly formula. It's on your formula sheet. You may have seen it before and questioned what it was. I wrote it down briefly when we first started this forces stuff. Just to review, remember, mass is stuff. It's the matter that an object is composed of, and it's unchanging regardless of your position. I don't even want to say relative to Earth. I would say in the universe. Whereas weight is the gravitational pull on an object towards, it says the center of the Earth, and I copied these out of a textbook, but really towards, let's say, another object, which may be the Earth. But really, it could be anything in the universe. It could be two of you out in deep space that have some weight, some force of gravity towards each other. All right, so limiting it to the Earth is really not the point of this lesson, so I'll make those two changes. Weight is therefore a force, and therefore we measure it in newtons, right? So I'm going to go pretty fast here because I can't see you guys writing and say, hey, does anybody need more time? So you guys are going to have to pause it when you need to. So weight, or the force of gravity, is going to be at a maximum when we're talking about near the Earth at the radius of the Earth. The radius of the Earth is 6.4 times 10 to the 6 meters. All right. But it drops off, as you can see, really quickly. It's actually an inverse squared relationship. If you guys know that in functions, it's like over r squared, where r is your distance away. So at 2 Earth radii, I should say, if you're 1,000 newtons of weight at the surface of the Earth, then at double the radius of the Earth, so just 2 Earth radii, you're going to drop all the way down almost to 200 newtons. You're going to get a significant drop off right away, but there is a line, there is an asymptote, if you like that word, at zero, meaning no matter how far, using Newton's universal law of gravitation, no matter how far I go away from the Earth in the universe, the force of attraction between the Earth and me will never ever reach zero. It's going to flatten right out and approach zero, but never reach zero. So knowing that it's an inverse squared relationship and knowing that this is the shape of the graph is of somewhat importance, but knowing exactly the positions and 2RE and 3RE and stuff like that doesn't really matter if you're thinking about note taking here, okay? The constant is called the universal gravitational constant with the symbol G. So this is the formula that's on your formula sheet, all right? So that capital G is not little g. It's not Earth's constant or gravitational field strength. This is called the universal gravitational constant, 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. Okay, if you want some context as to, okay, gm1 m2 over r squared, all right, here's m1, here's m2, and they are separated by some distance r. The only other variable, it's not even a variable, the only other thing in the equation is capital G, and we just discussed that. Now, it should be, I don't know, at least mentally noted that it's center to center, because you might think, well, we're 0 meters from the Earth when we're standing on the Earth. Well, that's not true. It's center to center. So we're actually 6.5 million meters from the center of the Earth. So that's the distance we are away. That's the formula, force of gravity for weight. Now, how do we get the gravitational field strength then, little g? Well, we have two formulas for gravity now. So at the surface of the Earth, or the surface of anything where we know the gravitational field strength, we have this from before. But now we have this, where it's m1, m2. You know, usually it's a big mass and a little mass. So instead of m1 and m2, I'm going to use big M and little m, and hopefully you guys don't get freaked out by that. Because that's going to work better in this little example here. So if standing on the Earth, both of these equations should be valid and give me the same weight. So that means I should be able to write mg equals g, big M, that would be the Earth's mass, little m, that should be my mass, divided by r squared. We've got an m, a little m on both sides, so they should actually cancel, which leaves me with a little formula here for gravitational field strength. And if we're to type in Earth's data, which capital G is that 6.67 times 10 to the negative 11, Earth's mass, I don't know if you know it, you don't have to memorize it, but I'll give it to you right here, 5.98 times 10 to the power 24 kilograms. And the radius of the Earth is 6.38 times 10 to the 6 meters, and we're going to square that. Now, if we type that data in, we should get about 9.8 newtons per kilogram or meters per second squared, because that's the gravitational field strength on the surface of the Earth. So this is something that's not on your formula sheet, but just something to mentally note that could help you out down the road. Pause it here if you need to. I'm moving on. So there's not a whole lot to this note. We just have to do some examples now. So it says, find the force of gravity between a sumo wrestler and a gymnast. We've got two masses, a big mass, a little mass, and a distance apart. So we just go at it with the formula. Fg equals g, big mass, little mass, over their distance apart squared. Now, I did mention I don't have a scientific calculator with me. Now, gymnasts and sumo wrestlers, we don't see them orbiting each other and falling into each other the way we do to Earth. So you're going to get an extremely small value for this, like times 10 to the negative, I don't know. It's going to be a small, small, small number of newtons, okay? So let's put in the data though. So 6.67 times 10 to the negative 11 times mass of the sumo wrestler, 300 kilograms, times mass of the gymnast, 40 kilograms, divided by their distance apart squared, 1.5 meters. So you guys are going to have to pause here and try and punch that in. And I'm going to write really small because I cannot do this in my head. And I'd encourage you to punch it in, get a number that's really small. Something times 10 to the negative 7 kind of rings a bell with me, but I can't remember for sure. But give it a try. And then pause and compare with somebody near you. If you get the same thing, it's probably right. And it should be really small because, people may or may not be attracted to each other, but it's not because of Newton's laws of gravity. Next one, I want to use both equations to find the weight of a 100 kilogram rugby player. So both forms of the equation, I mean, okay, so let's use Fg equals mg. Why? Because we have to assume this is on the surface of the Earth, so I can just go 100 kgs times 9.81 newtons per kilogram on Earth. 100 times 9.81 is 981 newtons. Now, if we're doing problems on the surface of the Earth and finding their weight, that's the way to do it. Why would you go through the other formula unless you're forced to, like we are here? So here's the big version of the formula: mass of the Earth, mass of the rugby player, divided by r squared. So that's going to be capital G. I'm not going to write it out because I'm going to run out of space, but it's 6.67 times 10 to the negative 11 times mass of the Earth, 5.98 times 10 to the power 24 kilograms. Mass of the rugby player, 100 kilograms. How far is it from the Earth? It's the radius of the Earth. 6.38 times 10 to the 6 meters squared. Now this one, again, I don't have a calculator, but I can tell you that it should be the same. It should be about 981. As a matter of fact, I think it rounds to 980 newtons because I've done this example a bunch. All right, so again, pause, type it in, and this one I can tell you, you did it wrong if you didn't get about 980. So get it or not. Last one I'm going to do with you today is this one here. 1,000-kilogram satellite is the payload on a planned shuttle launch. What is its weight? 32,000 kilometers from the Earth's surface. So it's going to be the same formula again. It's just plugging it in. The biggest challenge to doing these problems is just dealing with the large numbers involved. Punching scientific notation into your calculator. That's going to be your biggest challenge here. So I'm just going to show you. I'm just going to put S for satellite. So it's here, and E for Earth. It's going to be down here. Actually, I'm going to write E right here. So it says the satellite is 32,000 kilometers from the Earth's surface. Now that's 3.2 times 10 to the it's not 32,000, it's 32 million meters. So it's going to be times 10 to the 7 meters from the surface of the Earth. I was just trying to get it into scientific notation. Let me just make sure I did that right. 32,000,000 meters. Yep, I think that's right. Yeah, times 10 to the 7. But that's not going to be the distance from the Earth because we still have to include the radius of the Earth, which is 6.38 times 10 to the 6 meters. This year you don't have to have that memorized, and next year it actually comes included on the formula sheet if you take 4U physics. So the distance away, r, is going to be a combination of those things. I'm going to have to add them. 3.2 times 10 to the 7 meters plus 6.38 times 10 to the 6 meters. Now, even though I don't have a calculator, I'm going to have to just punch in that addition on my phone somehow. So it's going to be 3, 2, and 6 zeros. 1, 2, 3, 4, 5, 6. Plus 6, 3, 8. 4 zeros. 1, 2, 3, 4. Yep. Equals. There we go right there. All right. In scientific notation, I got 3.838 times 10 to the power of 367 meters. All right, so that's what I'm going to use for R. You have to pause it here because I might have to, and write that down because I might have to erase this later. So our force of gravity, again, is G, big mass, little mass, over R squared. So it's going to be G, that's 6.67 times 10 to the negative 11, times mass of the Earth, 5.98 times 10 to the power 24 kilograms, times how heavy is, or how, I shouldn't say heavy, how much mass is the satellite? 1,000 kilograms. And they are separated by a distance of 3.838 times 10 to the power of 7 meters. And don't forget that squared. Lots of people mess up by not squaring that. Now, I'm not going to attempt to punch that into my phone, so this again is a great spot for you guys to pause it Ask the teacher, the supply teacher, what he gets, or ask a friend that you trust what they got, um, and see if you can come with up with a consensus answer. So I'm gonna. You can pause it here and get to that point and get that taken care of. I'm going to get out of this PowerPoint though and discard my writing. I'm going to get into here and just show you the problems that you have to calculate, have to try today. Now, I really don't need you to do all of these, okay? What I would like you to do is to do number 20, 21, 22, 23, 24, 25. No. Yeah, I think you're good with just going to 25. All right. I think you'll have everything I need you to have if you just go 20 to 25. If you can do that, consider yourself good. I'm going to be at my computer. I don't mind making a video of even taking up questions. As a matter of fact, that's what I'm going to do for tomorrow and the next day is keep emailing me questions. It can even be off this, off stuff from last week, off the review that I posted on Monday. And I'm going to spend Wednesday and Thursday taking up any questions that you might have. All right. Let's see if I remember how to stop this. So, yeah, keep the emails coming. I already got about 5 questions that I'm going to include in the video that students have asked about, but keep them coming. And if I don't have enough time to get through them all in one period, I'll just keep rolling into the next period. And I definitely hope to be back soon. All right, that's all for now.